Hello everybody. Today we're going to discuss two ways to test a simple null hypothesis using the maximum likelihood estimator. We're going to be concerned with tests of this form. Suppose we have a simple null hypothesis that theta equals some fixed value theta naught versus the alternative hypothesis that theta is just equal to anything else, right? It's just theta does not actually equal theta naught. Right? And we're going to use two maximum likelihood estimator based tests. These tests are Wald's test, which is based on the asymptotic normal approximation to the maximum likelihood estimator. The second is the likelihood ratio test. The likelihood ratio test basically just looks at how much more likely is it that theta is in the null hypothesis versus theta not being in the null hypothesis set. Okay? After reviewing these two tests, we're going to look at a simple example where we have data drawn from this PDF. F of x given theta equals theta x to the minus theta minus 1, where x is greater than or equal to 1, and theta is some parameter that's greater than 0. So in this model, we want to actually estimate theta, right? And maybe do a hypothesis test with this theta. This is called the Pareto distribution, and has lots of scientific and economic applications. Okay. After we sort of look at this example and derive these two tests for this distribution, we're going to try to test, for example, a null hypothesis where theta equals some value. We'll pick theta equals 2 versus the alternative hypothesis that theta does not equal 2, right? So this would be an example where maybe you have some application and you expect the sort of parameter theta in your Pareto distribution to be 2, and you just want to see, does the data actually match this null hypothesis? Okay. After we derive the test, the two tests for these hypotheses, we're going to actually do the test where we observe an MLE of 2.45 with a sample size of n equals 100. And we're going to actually look at what do these two tests say for this data given these hypotheses. So as a review, what is Wald's test and what is the likelihood ratio test? Wald's test is based on the asymptotic normal approximation to the MLE. The asymptotic normal approximation for the MLE says that the MLE minus the true parameter times root n will converge in distribution to a normal with 0 mean and variance equal to the inverse of the Fisher information of the true parameter. Now notice that I can multiply both sides by the square root of the Fisher information, right? I get root n times root Fisher information times, again, the theta hat MLE minus the true parameter. What does this converge to in distribution? Well, since I've now scaled this term by the square root of the Fisher information, right, this converges to a normal 0, 1. And now if I square this term, right, it will converge to the square of a normal 0, 1. In other words, n Fisher information of theta times theta hat MLE minus theta squared will converge in distribution to the square of this, which is just the chi-squared 1 distribution. Okay? And now the other thing you normally do is when you have a statistic in this form, right, something that converges in distribution to something, you don't want too many parameters in this expression, so we'll actually use a plugin, and this will define Wald's test, right? So plug in for the standard deviation portion of this normal variable, and we get this convergence, right? It still works. So this is Wald's test. We're going to use this statistic and its asymptotic distribution to derive a test for testing this sort of hypothesis. Now the likelihood ratio test basically looks at how much more likely is, say, the alternative hypothesis when compared to the null hypothesis. To do this, you look at the likelihood ratio, right? It just says it in the test. The likelihood ratio will be the likelihood of your data given, say, the alternative hypothesis over the likelihood of your data given the null hypothesis. Now in the alternative hypothesis, right, theta can take a whole range of values. So we'll just say that this is the maximum of theta in the alternative set, theta 1, right? We'll call this set the set theta 1. So this will be our likelihood ratio statistic. And basically when the alternative hypothesis is a lot more likely than the null hypothesis, we want to reject the null hypothesis. In other words, when this is much greater than 1, right, greater than some constant determined by the significance level of our test, and that constant's of course greater than 1, then we will reject the null in favor of the alternative. Okay? Now, since this is a maximum over an open set, you should actually write sup, right? The sup will be basically the maximum over the closed set here. And then if you look at least in this case, right, the maximum over this whole range of thetas will just be the maximum likelihood estimator. In other words, this likelihood ratio is the likelihood of x1 to xn given theta hat MLE versus the likelihood of x1 to xn given the null value theta naught. And this is, of course, greater than some constant greater than 1. Now, the version of the statistic that you saw in class actually was basically the log of this. So if I take a log of both sides and multiply by 2, I get this, right? You'll see why in a second. We multiply by 2. Okay, so if I took a log, I get the log likelihood of the MLE minus the log likelihood of theta naught, right? And this is going to be greater than log C, which is just some positive number, or it's just some number. And the reason we look at this is we have a theorem called Wilks' theorem, which states that this statistic here, based on the MLE and the null hypothesis theta naught value, will converge in distribution to a chi-squared 1 distribution. So as you can see, you can actually derive two tests that have asymptotic chi-squared distributions. One is Wald's test, which is based on the square of an asymptotic normal approximation. The other is a likelihood ratio test, which looks at basically the comparison of the likelihoods of the alternative hypothesis and the null hypothesis. And basically, when you take a log and multiply it by 2, you can show that you actually do get this asymptotic chi-squared approximation. In the next part, we're going to actually calculate these two statistics for this example, the Pareto distribution.